All right, so again, we're in part D of our discussion packet. That's page 4. What we're going to be looking at today is how to solve for an unknown variable. Pressure, volume, number of moles, right, or number of particles, or temperature. Before I go through and talk about each, right, how to solve each problem, I want to go through and look at the summary of the relationships. Now, we've looked at this already, but this is a way that you have everything right at the top of the page. So, summary of the relationships. I just want to know, like, as one goes up, what happens to the other one. So we're just looking at direct or inverse. So we have it right here, quick and easy. So remember, pressure and volume. We think about volume. As volume increases, as volume gets bigger, what happens to our number of collisions? Goes down. So pressure decreases. Pressure and volume is the only inverse relationship that we look at. It's the only one that's opposite. The reason we're going over these relationships again is because it's going to be useful when we start looking at the math. Pressure and number of particles. So pressure is P. Number of particles is actually represented with the letter N. So that's going to be useful as we start to get into everything. When you see the letter N, that actually stands for number of moles. Could be number of particles as well. So if we think about this, as number of particles increases, we have more collisions, so pressure increases. That's a direct relationship. Remember, I said the only inverse relationship is P and V, meaning everything else is direct. So as one goes up, the other goes up, or as one goes down, the other goes down. So pressure and temperature, let's say temperature goes up. Well, that means that number of collisions goes up, so that's direct. Now, instead of up, this could be down, right? So maybe I said temperature goes down, that means pressure goes down. You could have either way. And then volume and temperature, this one is a little bit difficult to think about because pressure must stay constant. So since pressure must stay constant as you increase temperature and your particles start to move faster, you need to increase the volume to keep the pressure constant. So again, direct relationships. So what we're doing here is we're looking at all the relationships between the variables. We need that as we start to get into these gas law problems. So as we look at actually solving for pressure or volume or number of moles or temperature. Now what we're going to do for each of these problems is we're going to set up something called a PVnT table. And I'll show you what that looks like. We have a PVnT table that allows us to kind of organize all of our information. So normally, if you were to read a textbook, they would give you 4 or 5 different equations to memorize. All the equations are different. They're going to be solved differently. But instead of having to memorize 4 or 5 equations, we just use one of these PVnT tables to organize all of our information, to think about, okay, what's the effect on all of these variables? And then we find an easy way to solve. So we're going to set up what's called a PVnT table. We're going to fill in all of our information. What's the initial information they give us? What's the final information that they give us? So we're going to start by looking at number 1, right? We're going to go through these 3 steps. We're going to solve a few of these problems together, and I am going to have you try some on your own. So we're going to look at number 1. This says, what would be the new pressure? Now what I like to do as I solve problems is I like to label everything with variables. So what would be the new pressure if 250 centimeters cubed? Now, we talked about this at the very beginning of the year. Centimeters cubed is actually the same as milliliters, so I'm just going to label that milliliters instead. Something that we're used to seeing a little bit more than centimeters cubed, but that's a volume, amount of space something takes up. At standard pressure is compressed to a volume of 150 centimeters cubed. All right, so again, centimeters cubed is milliliters. So we have a volume here, a volume here. And then they also say at standard pressure. So we've talked about standard pressure before. All of those pressure conversions that we did, those are all standard pressures. That means that 1 atm is standard pressure. So I'm just going to label it 1 atm. So in all of these problems, what they do is they give us 2 sets of conditions and we have to find an unknown variable. So when we do this, I'm going to set up a PVnT table. This is what a PVnT table looks like. I have pressure, volume, number of particles, and temperature. And I make a table that I'm going to fill in. I'm going to go straight across. Now within the PVnT table, I have 3 rows. I have initial, I have final, and I have the effect. And we're going to actually fill this in. Now, we're not always going to fill in every single one of the spots on the table. I'm going to look at what the problem gave me, and sometimes I have to read it a couple times. So it says, what would be the new pressure? So they're asking me about pressure. They're asking me about new pressure. So they're asking me, what's the final pressure going to be? I'm going to put a question mark in the final pressure box. If 250 milliliters of gas at 1 atm. So I have a container of gas. I'm just going to draw a little particle diagram over here so we can kind of think about what we have. So I have a gas. I'm going to just draw 4 molecules in here. It's 250 milliliters of gas. This container's at 1 atmosphere. It's at standard pressure. It wants to know what's going to be the new pressure if I compress it down to 150 milliliters. So if I'm making the volume smaller, it wants to know what's the actual value of pressure. So now we're not just looking at, oh, it's going to go up or it's going to go down. We want to put an actual number to it. So I'm going to fill this in now. My initial pressure of this gas is 1 atm. So initially the gas is at 1 atm. And that gas is in a 250 milliliter container. Now it says that it's compressed down to 150 milliliters, so my final volume is 150. Now this problem says nothing about number of gas molecules and says nothing about temperature, so I'm going to put a big X through both of those. Number of particles and temperature doesn't matter. Right? It doesn't say anything about it. So now here's the effect. I want to look at what happens to the volume here. From initial to final, the volume goes down. Now is where those relationships come in. If the volume is going down, volume is decreasing, what do we expect in general will happen to the pressure? It's going to go up, right? So I'm going to put an up arrow with a little V next to it. What that tells me is the pressure should go up because of the volume changing. Now here's how we actually solve the math problem. We're solving for pressure. So start with your initial pressure. I'm just going to write it over here off to the side. The initial pressure is 1 atmosphere, 1 atm. Now what we need to do is we need to multiply by a fraction. We're multiplying by a factor. My factor is going to be the 2 numbers within volume. So really I'm either multiplying by 250 over 150 or 150 over 250 based on what you want to happen to this number. If I want pressure to go up, should I multiply by a big fraction or a small fraction? You want it to go up, I'm going to multiply by a big fraction. So to solve for this new variable, right, we're solving for final pressure. You're multiplying by a fraction. This fraction comes from our volume. Now to solve this, we solve this just like we've done before. Right, here's how I would solve this. I'm going to do 1 times 250 divide by what's on the bottom. Divide by 150. You get 1.6 repeating. So if I want to round to, say, 2 decimal places, 1.67. 1.67. Now just look at your initial unit of pressure. Atmospheres, our answer's in atmospheres. So the PVnT table just allows you to organize all of your information. Pressure can be in any unit as long as they're the same. Volume can be in any unit as long as they're the same. Number of particles, any unit as long as they're the same. The only one that we absolutely have to change is temperature. Right? Temperature has to be in Kelvin because sometimes you're going to notice that you're given negative degrees Celsius. You can't have negative temperatures when you're dealing with gases. So you always have to convert to Kelvin. So what I want to look at next is I want to actually come down to number 3. So we're going to kind of skip around. I want to look at number 3. When you notice that you have a problem that has multiple of the same variable, so 2 pressures, 2 temperatures, 2 number of particles, we're going to set up a PVnT table. We have initial conditions and we have final conditions. So I'm going to start by setting up the PVnT table, and you can make it as big or as small as you need. Right, you can make it as big or as small as you need as long as you can fit your numbers in here. So I have initial, I have final, and I have effect. Now I go through and I read this problem. The pressure in a bicycle tire is 105 psi. All right, so the pressure in a tire is 105 psi. So in my initial pressure, I'm going to put 105 psi. It says at 25 degrees Celsius. Now I'm going to write the temperature over here to the side because we just said that to plug in temperature, it must be in Kelvin. Remember, to go to Kelvin, just add 273. K equals C plus 273. So just add 273. So the initial temperature is actually 298 Kelvin. Then it says you take the bicycle up a mountain. All right, so you ride the bike up a mountain. Now it's -5 degrees Celsius. So now the final temperature is -5 degrees Celsius. Again, notice how they give negatives. You cannot have a negative in your math problem. You can't have a negative pressure or a negative volume. That's why we have to convert. So again, add 273. So, what is that, 268? Now it says, what is the pressure in the tire? So it wants me to solve for the final pressure. Put a question mark under final pressure. Again, this problem said nothing about volume, nothing about number of particles. So I'm going to put a big X through it. There are times that we're just comparing 2 variables. So now, look at what happens to temperature. It goes from 298 to 268. So it goes down. Temperature goes down. This effect row is taking into account the relationship between the variables. So as temperature goes down, the molecules move more slowly. What does that do to pressure? Also goes down. So now the effect under pressure, I'm going to put a down arrow due to temperature. So my final pressure should be lower than my initial based on the variable relationship. Now to solve, start with your initial value. Since I want to find final pressure, I need to start with initial pressure. Now I'm multiplying by a factor. This factor is based on these 2 temperature numbers. I want pressure to go down. If I want pressure to go down, my options are 298 over 268 or 268 over 298. If you want your number to decrease, you should multiply by a smaller fraction. To multiply by a smaller fraction, I'll do 268 over 298. Now, if you don't believe me, go the other way, and then you're like, uh-oh, my pressure went up. Then you know to flip that fraction. So to solve, I'm going to do 105 times 268 and divide by what's on the bottom. You could do 94.4. You could do 94.43. I'll just do 94.4. Your pressure unit is the same as your initial pressure unit, PSI. Now do a quick check for both of these questions that we've done. We said pressure should go down in number 3. It went from 105 to 94.4. It went down. In number 1, we said pressure should go up. It went from 1 to 1.67. It went up. So this is looking at what happens if we're comparing two numbers, right? Two variables. I want to look at one more, right? What happens if we have more than two things? So I want to look at number 5. We will come back to these other examples, right? We will come back and we'll work through all of them. But I want to look at number 5. So this says Joe's bike tire contains 15 units of air particles and has a volume of 160 milliliters. Under these conditions, the pressure reads 13 psi. Then the tire develops a leak. Now it contains 10 units of air and has contracted to a volume of 150 milliliters. What would the pressure in the tire be now? So now, again, we have an initial set of conditions and a final set of conditions. So I know I'm going to need to set up a PVnT table. So I'm going to set up the PVnT table. It always looks the same. Initial conditions, final conditions, and the effect. And now sometimes you have to go back through and read the question to plug into the PVnT table. So initially, Joe's bike tire contains 15 units of air particles. There's the number of particles. That's N. So I'm going to put 15 in for N. Has 15 units of air. And it says it has a volume of 160 milliliters. So initially the volume is 160 milliliters. Under these conditions, the pressure is 13 psi. So there are initial conditions. After the tire develops a leak, so now here's our final set of conditions. It has 10 units of air. It now has a volume of 150 milliliters. What would the pressure be? So I'm going to put a question mark for final pressure. This said nothing about temperature, so I can put an X through temperature. But now we have two variables changing, and both of those are going to affect pressure. So let's look at N first. Number of particles. Number of particles went down. If the number of particles goes down, what would that do to pressure? Go down. Less particles, less collisions. So now, in the effect, I'm going to go down with a little n next to it. So pressure should go down due to the number of particles. But now we also have volume changing. Volume goes from 160 to 150. Volume goes down. Now I want to think just about P and V. Ignore N for a minute. Just think about pressure and volume now. If volume goes down, what would that do to pressure? It'd go up, right? That's the only inversely related set of conditions. So I'm going to also put an up arrow under pressure with a little V next to it. So now what that's telling me is pressure should go up due to volume, but down due to number of particles. So this is what this looks like when you have two variables changing. Still start with the initial of what you're trying to solve for. So if I'm trying to solve for pressure, I'm going to start with initial pressure, 13 psi. Now, because I have two variables changing, I'm going to be multiplying by two fractions. I'm going to have two fractions that I'm solving for. One of them is due to volume, and one of them is due to number of particles. So over top, I'm going to put a V and I'm going to put an N. We said that pressure should go up due to volume. So if I want pressure to go up due to volume, I'm going to put a little note under here. P should increase due to volume. If pressure should go up due to volume, I need to multiply by a large fraction, right? A large numerator, or at least the numerator should be larger than the denominator. So that means if I'm just looking at volume, I'm going to do 160 over 150. Because pressure should go up based on the relationship between it and volume. But now if I come over to N, we said that pressure should go down. So pressure should decrease due to N. So that means if I want the number to get smaller due to the number of particles, I need to multiply by a fraction that's going to make it smaller, so a smaller fraction. So my option for N is either 15 over 10 or 10 over 15. If I want a small fraction, that's 10 over 15. Now to solve, multiply across the top, 13 times 160 times 10, and divide everything that's on the bottom. So I'm going to do divided by, and I'm going to use parentheses, 150 times 15. We get 9.24. So my answer is 9.24 psi. So it's still done the same way if you have multiple variables changing. You're just going to have two fractions that you're multiplying by instead of just one. So for every single one of these questions, you can set up this PVnT table to see what are the initial conditions, what are the final conditions, and how do they cause the variables to change. So let's flip back, and let's see if you can at least set up the PVnT table for number 2. So if we flip back to number 2, see if you can read through and set up the PVnT table. Just fill in the initial conditions and the final conditions.